In this video, we're going to continue our talk on colligative properties, and we're going to begin with the idea of ideal and non-ideal solutions. So in the previous two videos, we used Raoult's law to determine pressures, vapor pressures of solutions. However, that's only for ideal solutions, and in the world, no solution is really ideal. Basically, what an ideal solution is when you dissolve something, the interaction between a solute-solute molecule, a solvent-solute molecule, and a solvent-solute molecule are all the same. So it really doesn't matter what type of molecules you have, all interactions are the same. It's the same strength in an ideal solution, which is never the case in reality. So the solute is diluting the solvent, basically. But if you have interactions, like if solute-solute interactions are stronger than solute-solvent, for example, if you have some kind of uneven interactions, you have non-ideal solutions. And so vapor pressure changes. So here are three plots. And at the first plot we have our ideal solutions. So the way to read this plot is the red line is the partial pressure of your component A. So we could think of this as chloroform as in the previous example. Blue, partial pressure of your second component, so acetone. Purple is just the solution. So you can see it is perfect. That's ideal solution. But if you have non-ideal solutions, for example, if your solution has very strong solute-solvent interactions, that is, whatever you dissolve in your solvent interacts very strongly with that solvent, for example, ions, then the vapor pressure of the solution is lower than you would imagine, while if you have very weak solute-solvent interactions, then the vapor pressure will be greater than you calculate. So for non-ideal solutions, we can't actually use Raoult's equation and Raoult's law to get a perfectly exact answer. But for any problems we do in this course, we're going to assume, unless told otherwise, but we're going to assume this solution is ideal. Now let's look at three other colligative properties, and we're going to start with two here. Melting point and boiling point. So when we dissolve something in a solvent, the melting point will decrease and the boiling point will increase. So here, blue line is pure solvent, red line is solution. What that means is it's harder to freeze something. You need to get to a lower temperature to freeze something, and it's harder to boil something. You need to get to a higher temperature to boil something. And that's why we use antifreeze in our cars. Antifreeze will make sure that your liquids don't freeze. It's harder for them to freeze because antifreeze is made out of ethylene glycol. It will form a solution. It is a solution, so it lowers the freezing point. So let's look at this mathematically. Like I said, freezing point lower, so it's harder to freeze something. And the freezing point in a solvent, in a solution, is given through this equation. So freezing point of a solvent minus the freezing point of a solution, that is the change in freezing temperature, and that is equal to the molality of your solution multiplied by Kf, which is a constant. Remember, molality, weight of your solute divided by, moles of your solute divided by weight of your solution. That is molality. Kf is your freezing point depression constant, and it's depending on the solvent. The units are centigrade divided by molality. So if you have your molality, your answer should be in centigrade. And boiling point elevation is very similar to freezing point depression and has a very similar equation. boiling point of a solution minus boiling point of a solvent, what we call that delta TB, equals the molality of your solution multiplied by Kb. And Kb is our boiling point elevation constant. Again, it's a constant you will be given or you will be asked to solve for. And it's dependent on the solvent. And the units are degrees centigrade divided by molal. And the next colligative property we're going to look at is osmotic pressure. And to talk about that, we first need to talk about osmosis. And osmosis is the movement of a solvent from low concentration to high concentration. So here we have two solutions. One is salt water and one is pure water. And they're separated by a membrane that only lets water across. Well, naturally, the water with no salt will flow to the water with salt until the concentrations of salt are the same. And the pressure difference is the osmotic pressure. So eventually, they're going to flow, and gravity is pushing down on each side. And this difference in height is what we call the osmotic pressure. And we can calculate this difference in height or osmotic pressure through this equation. So this symbol, capital Pi, is the osmotic pressure. And it's equal to molarity of solution multiplied by the gas constant and temperature. As long as we have molarity, gas constant, and temperature, we can find osmotic pressure. Or if we have osmotic pressure, we can calculate molarity. And that's it for this video. I'll see you in the next video.